So we're going to begin looking at collisions. Collisions generally involve situations where you have two or more, but generally at least two, and a lot of problems there will be two, objects who are, at least one of them is moving prior to, and they're separate from each other, and then they hit each other, and then they react afterwards. Now, keep in mind, there's lots and lots of possibilities here. You could have the simple situation of one object moving and hitting another object that's stationary. Of course, what happens after they hit? Well, do they stick together and blob into one object and have a momentum after that? Or do they bounce off each other in some way, continuing to remain as two separate objects? That's basically the two types of equations we're going to look at. Types of collisions we're going to look at. One, where objects stick together. So any collision where objects stick together is called, that's what we're going to look at first. So if the objects stick together, two train cars hitting each other and coupling, or a piece of clay hitting something, or a football player gets tackled and the two of them, one wraps the other one up as they go down. These are situations you'll run across probably. But if objects stick together, they don't bounce off, in other words, we call it inelastic. That is an inelastic collision. In an inelastic collision, momentum is conserved, but kinetic energy is not conserved. I guess that's not a great way to phrase it, but, we can do it this way. Kinetic energy initial won't be equal to kinetic energy final. So one of the characteristics of inelastic collisions is kinetic energy isn't conserved. There might be a lot of kinetic energy in the beginning and probably less afterwards. In fact, certainly less, because you'll have some heat when the objects deform, you'll get some energy lost to that. The other type of collision, and those are generally, I think, a little simpler to deal with because you only have one object afterwards. You can see it's kind of the opposite of what we've been looking at in the earlier videos. If the objects bounce off of each other, then we call that, you're probably already there, an elastic collision. Now, elastic collisions, one of the key features of that is kinetic energy is conserved. I'm going to point out now that this is a theoretical, we're going to look at perfectly elastic. In other words, there is really no such thing as a perfectly elastic collision, but there are certain circumstances where we don't have to worry about how much energy is lost in deforming the objects as they hit. Think of like a cue ball hitting another billiard ball. Technically, they do bend a little bit, and then when they push off, there's a little bit of energy loss. The balls will be warmer, but that one is so little energy is lost that way that would be a good example of something we could model at least as an elastic collision, a perfectly elastic. So if a problem says that it's an elastic collision, or two objects collide elastically, the kinetic energy at the beginning will be equal to the kinetic energy at the end. So that's good. That means we have more information we might be able to work with or use. The problem is if you think about it, if you have two objects and they collide, doesn't matter, they could be moving in any number of different ways, by the way. One could be moving this way, the other could be at it. One could be stationary. You could even have one where this one's moving fast and this one's moving slower that way. They're still going to collide. All those would be examples. But if they bounce off each other and you have two objects after the collision as well, then you have what is probably going to be considered an elastic collision. But we're going to start in this video, we're going to focus on inelastic. So we're going to focus on that. And what we'll do is, I think probably the best way to look at it is through a problem. So this problem actually involves momentum, and it's going to involve some energy at the end, which is good. It's a good chance for us to practice both. but we're going to focus mostly on the momentum here at the beginning. So, like every other momentum problem, I highly recommend looking at the before situation. And if you'd like, we can do the after over here. So, in this problem, as you read it, a bullet is moving and hits a wooden block in something called a ballistic pendulum. So this is a device they use to measure the speed of bullets. The ballistic pendulum involves a wooden block that is free to rotate. The bullet will come in with a velocity, and so therefore it has a momentum, and it will hit and embed itself in the wooden block, which, because it was just hit by the speeding bullet, will start to move. Not as fast as the bullet was, right? Because the mass just went up. But the bullet will embed itself in the block. The block will then start to move with a velocity. And this is the after final velocity, for example. So here's the initial velocity of the bullet. The initial velocity of the block, let's go BL for block, is of course 0 in this case. Afterwards, the final velocity is for both because they're now one object. And then that pendulum will swing upward, and conservation of energy will tell us something about it when it swings up like that, how high it went. We can turn that kinetic energy here into potential energy here, and you can see where the energy part might come into this later on in part B. But for now, all we're going to concern ourselves with is this. After the collision, so right after, immediately after the collision, that block has a velocity as well. There is a momentum of a final momentum, which in this case would combine the block and the bullet. Here, in the beginning, that momentum, the initial momentum, is all possessed by what object? All that initial momentum is in the bullet since the block is at rest. So considering all that, we always start with forces are internal because our system is going to be the block and the bullet combined. So the initial momentum is equal to the final. Initially, we have two objects. I'm going to write this out a little bigger than I would normally. I know the momentum of the block is 0, but I don't want to jump to that too quickly because there could be plenty of situations where it's not. So if I have two objects, I'm going to write the momentum for each. I'm going to say the mass of the bullet times the velocity of the bullet initially plus mass of the block, BL, times the velocity of the block initially equals, so there's two parts to that momentum initially. And I know, I get it, that in this problem, I know this is 0 because that velocity is 0. But just stick with it because this will help you with all problems, not just one where one of the objects is stationary. Afterwards, they are now one combined object. So the mass of the bullet plus the mass of the block, and they have a final combined velocity because they are now one object. So here, notice it's the exact reverse of the situation we've looked at earlier where a single object breaks apart. Now in this case, like we mentioned, since that initial velocity of the block was 0, it was just sitting there, we can get rid of that term. And so what I really have is the mass of the bullet times the velocity of the bullet originally equals mass of bullet plus mass of block times final velocity. Now, this final velocity that sits right here, that is what they are asking for right here. They want find the speed of the bullet block combination right here immediately after the collision. They have to say immediately afterwards because when this thing starts to swing up, some of that, its kinetic energy is going to start turning into potential and it's going to slow down. So they want to know right after they collide, what is that, basically that starting velocity as it begins to go up. So the ending velocity for the collision part of this problem becomes the starting velocity for the energy part. So you want to keep that straight as we go through here. Okay, so for us, we're looking for that final velocity, so it's going to be mass of the bullet, velocity of the bullet originally, divided by mass of bullet plus mass of block, equals the final velocity of the block. Well, final velocity of the block and bullet combined. So in our case, we can go ahead and plug that in, find that final velocity after the collision. But now, we're going to rename that final velocity, because now for part B, we're going to start looking at the energy. So this is now going to be called the original velocity for the energy part of this problem. So now, I don't care how the block started moving. All I know is that I have this object on a pendulum, and it's moving, and it's going to swing up until it stops. So for the energy, this is the initial, right after the collision with the bullet, and this is the final. So my final velocity, once again, from the first part of the problem, is now renamed and called the original velocity for this part. So what kind of energy do I have down here? Well, if we assume that this level is where h is 0, and that the final height here is something other than 0, then we don't have any spring energy. There's none of there. We have no gravitational potential energy because we're at the lowest height possible, so we must have all kinetic energy. And all of that kinetic energy is going to, as it slows down, when it stops up here, all of that kinetic energy is now in the form, well, not spring energy, it's in the form of gravitational potential, because we would have lost all of our kinetic because it would stop at that point. So think about what you know. You know the mass of the total mass of the two of them, right? The bullet and the block combined, because they're now one object. So the kinetic energy down here is going to be 1/2 that total mass. You'll forgive me, I'm going to write total mass. That's right here. That would be these two combined. Times the velocity squared. Remember, that's the velocity you found here, which has now been renamed the original velocity of the block before it goes up. That kinetic energy, you're going to set it equal to the gravitational potential energy up here. So, kinetic energy at the start is going to equal the, in this case, the gravitational potential at the end. So I'm going to have 1/2 total mass times that original velocity squared equals total mass times g times the height to which it rises. Well, the cool thing is the mass doesn't matter because it's going to divide out. Let's see, I got 1/2 that original velocity squared equals gh. I can divide by g, and that should tell me the height. I assume that's what they're asking for. So I'm going to look at that as VO squared over 2g equals the height to which it went. Let's see if that's what they're asking for. Yes, it must be meters. It's in meters, so I'm assuming it is. How high does the combination? Yep, that's what they're looking for. So there's a run through on that problem. So this is energy here, but it's good to know that. You're going to get a lot of situations where they start combining things like that. But where for us, the momentum is the new part, is how to handle a situation like that. So remember, if you have a problem later on, this may not, if you have two objects, one of them may not be stationary. So you may have one of them have a positive momentum, for example, and the other one be moving at it, which means it would have a negative momentum. So keep that in mind, is that you don't have to have zero momenta here. One of them could, both of them could be numbers. Some can be negative, they may both be negative. They could both be positive. All kinds of possibilities there, so keep that in mind.